So, good afternoon, everyone. I welcome you all in this lecture series on GATE in civil engineering under the banner of PRERANA Scheme. As you all know, in the previous classes, we have done your subject related to surveying and we have discussed various topics. Today's topic is your theodolite traversing. So, theodolite is an instrument which is basically similar to your compass. In this instrument, what is happening is that we can directly measure your vertical as well as horizontal angle. Okay. The only difference in compass and your theodolite is that we can measure your angle with higher accuracy as compared to your compass. Okay. uh, this is the syllabus which we are going to discuss in this lecture. That is the objectives behind using theodolite surveying, various parts of your theodolite, some technical terms, how you can do the temporary and permanent adjustment of your theodolite, and how to measure the horizontal and vertical angle. What are the various methods adopted while performing your theodolite traversing? There are called as namely repetition method, retracement method. Okay, and after that you can also calculate the latitude and departure by using your theodolite. Okay. After that, there will be balancing of traverse, how you can balance the traverse perfectly by using your transit rule, third rule, and modified transit rule. And we will also do some of the numericals related to some missing data. Okay, so this is all about the syllabus which we are going to discuss. Okay, so initially we will start with the introduction of theodolite. Basically, a theodolite is an interesting instrument which is basically used to measure, as I've told you, it is generally used to measure what horizontal and vertical angle, and you can measure an angle up to what 10 second, okay, or 20 second, okay, depending upon the least count of your theodolite. Okay, previously we were using compass and we were able to measure only 30 minutes angle. Okay, with the help of theodolite we can measure up to 10 second. Okay, or 20 second, depending upon the least count of that instrument. Okay, it is also used for various purposes. Okay, it is not necessary that it is will be always used for measuring horizontal angle or vertical angle. It has some other purpose also, therefore it is also sometimes called as your universal instrument also. Okay, this is a picture of your theodolite. Okay, you can see that it consists of a plate on which you can measure your horizontal angle. It also consists of a top plate on which you can measure a vertical angle. Okay, there is a telescope provided so that you can see the object which is far from your point. Okay, after that, as I've told you that it is not necessary that it is always used to measure only angles. It is used for various purpose. Some of the purposes are, it is used for measuring horizontal angle, vertical angle. It can also be used to what, measure deflection angle. Okay, then it can be used for measuring magnetic bearing. Okay, after that, measuring the horizontal distance between 2 points, you can measure the distance between 2 points. Then if we want to find out the vertical height of an object, that can also be possible with the help of theodolite. And if you want to find out the difference of elevation between 2 points, you can easily calculate with the help of your theodolite. Okay, and then ranging is also possible with the help of your theodolite. Okay, so these are some of the purposes for which you can use your horizontal angle, vertical angle. Okay, deflection angle, it can be used for magnetic bearing, it can be used for horizontal distance between 2 points, for vertical height of an object, and difference of elevation, and also for ranging. Okay, after that, mainly there are two type of theodolite which are currently present in the market. One it is called as your transit theodolite, one it is called as your non-transit theodolite. What is the difference between transit and non-transit theodolite? If suppose we are using transit theodolite, okay, it can be revolved completely about its horizontal axis. Okay, so transit theodolite can revolve around its horizontal axis. Okay, in by definition, in the transit theodolite, the telescope can be revolved through a complete revolution about its horizontal axis in a vertical plane. And in case of non-transit theodolite, the telescope cannot be revolved through complete revolution in your vertical plane. So this is the difference between your transit and non-transit. It can be revolved completely. It cannot be revolved completely in the vertical plane. This is the main difference between a transit and non-transit theodolite. Okay, so this is a picture of your transit theodolite and a non-transit theodolite. Okay, the left one is your transit theodolite, and the right one is your non-transit theodolite. After that, some of the definitions which are important while you're performing your theodolite traversing. First one is your centering. So you whenever you are doing your theodolite traversing, you need to mark a station. Okay, okay. On that, you will have to install your instrument, and the first step is to do the centering. Centering is done with the help of what? The setting of theodolite exactly over the station mark by means of plumb bob. So basically, what you are doing with the help of plumb bob, we are marking the station which is exactly on the ground. Okay, matching the center of your theodolite with the center of your point. Okay, it is generally done with the help of a plumb bob. Then after that, transiting, the method of turning the telescope about its horizontal axis in a vertical plane through 180 degrees is termed as transiting. So basically, what you are doing is that you are turning the telescope through 180 degrees. Suppose if you want to take an angle in the front, if you want to take a measurement in the on the front side, and after that you will have to take a observation on the back side. Then you will have to turn the telescope through 180 degree, and that process is called as your transiting. Okay, then there is face left and face right position. So as I've shown you in the picture, uh, so as you can see in this picture, a vertical circle is provided on the left hand side of the telescope. So this means that this position is called as your face left position. Okay. So if you are taking your observation with the help of your telescope and the vertical circle is on the left hand side, then it is called as face left position. And if the vertical circle is on the right hand side, then it is called as your face right position. Okay. After that, changing the face. So if you are what operating, basically if you are changing the face from left to right or from right to left, that is process is called as your changing face. Then there is swinging the telescope. So this indicate that if you are turning the telescope in horizontal plane, suppose if you are swinging it in the clockwise direction, then it is called as your uh, right swing. Okay, and if you are turning it into anti-clockwise direction, it is called as your left swing. Okay. After that, there are some of the other definitions like line of collimation. Okay, so the line which is passing, suppose you can see this diagram. ऐसा change नहीं हो रही है, इसको change ही नहीं हो रहा है, लेट हो रहा है लेकिन थोड़ा. Okay, so in this diagram you can see that this is your telescope, and the line which is passing from the center of your telescope, it is called as your line of collimation. Okay. After that, there is axis of the telescope. Okay, so the axis is an imaginary line passing through the optical center of the object glass and the optical center of the eyepiece. Okay, so it is similar to your line of collimation. You can see that this is your object glass, this is your object glass, this is your eyepiece. So the line, imaginary line which is passing from the center of the eyepiece and the object glass is called as your axis of your telescope. After that, there is access of the bubble tube. So access of the bubble tube, basically it is a tube, a level tube has been provided on the top of your telescope. Okay, so the line which is parallel to that bubble tube is called as the axis of the bubble tube. Okay. After that, there is a vertical axis. So along the vertical axis, you can see that your whole telescope can revolve. Okay, so this line is called as your vertical axis. Okay, along which your telescope completely revolves through 180 degree or 360 degree. Okay. Next one is your horizontal axis. So horizontal axis is what around which your telescope can rotate in vertical plane. Okay, so as I've told you, it is an instrument which is used to measure horizontal as well as vertical angle. So it is necessary that it should move in horizontal plane as well as in vertical plane. So in vertical axis, it revolves around the horizontal plane, and uh, in your vertical plane, it can revolve around the horizontal axis. Okay, after that, whenever you install your instrument at a point, you need to perform certain adjustment. Okay, that is called as your temporary adjustment. So the setting, if the theodolite over a station at the time of taking any observation, it is called as your temporary adjustment. Okay, after that, uh, permanent adjustment is what, when the desired relation between the fundamental lines of the theodolite is disturbed. So then some procedures are adopted to establish this relation. This adjustment is called as a permanent adjustment. So basically, why you have to do permanent adjustment is that, suppose if you are continuously using your instrument, okay, and you're handling it continuously, so what will happen? There are certain relation between the access which has been provided in the telescope. So basically, because of heavy use, they get disturbed, and for that purpose, you will have to perform a permanent adjustment if they are disturbed. Okay, so this is the difference between temporary and permanent adjustment. Okay. After that, diaphragm. Okay. So whenever you see through your telescope, you will find a circle. Okay. Diaphragm, which consists of a brass ring. Okay, which is called as your crosshair. Okay. There is a photo of this. You can see that when you see through your telescope with the help of eyepiece, there is a diaphragm provided, circular diaphragm, which consists of hairs. Okay. This is your vertical hair. This is your horizontal hair. There might be different crosshairs depending upon the company of the instrument. Okay, this is one type, this is another type, this is another type, this is another type. Okay, after that, this is the whole assembly of your transit satellite. Which part what is the different features. This one is called as a vertical axis. This is your objective, this is your telescope altitude, this is a vertical clamping screw, this is the tuning vertical screw. Okay, this is the eyepiece, plate level, upper plate, vernier, lower plate, inner spindle, outer spindle, tri-back, leveling, tripod, tri-head, and tripod. So we'll study about the each parts in brief. Okay, first one is your foot screw. Basically, the whole instrument has been set up upon foot screws. Okay, so while performing your theodolite, what you have to do is that you have to make the line of collimation perfectly horizontal. Okay, for that purpose, foot screws are provided. This foot screw can be used for making the line of collimation perfectly horizontal. Okay, so that is the purpose of your foot screws. Then there is tryback. It is a triangular plate carrying three foot screw at its end, so the foot screws are being provided on this tryback. Then there is leveling head. The tribord, foot screws, and the tribord consist of a body which is known as a leveling head. So this all together, this assembly together is called as your leveling head. Okay. Then there is spindles. The spindle consists of two spindle or axis. One it is called as the inner axis, and another one is your outer. The inner axis is solid and conical, and the outer is hollow. Okay, so the inner one is your solid and conical, and the outer one is your hollow. Then there is a lower plate on which your horizontal angle can be measured. The graduation which has been marked is from 0 degree to 360 degree. Then there is upper plate, okay, which is provided in the vertical circle. The upper plate consists of a vernier A and B. It is attached to the inner axis. The motion is controlled by the upper clamping screw and the upper tangent screw. So with the help of upper clamp screw and upper tangent screw, you can control its motion. When the clamp screw is tightened, the vernier scale are fixed with the inner axis, and for fine adjustment, the scale, the tangent screw has been rotated. So this is the diagram of your spindles. How is your lower plate has been attached to your upper plate? Okay, this is the clamping screw. Okay, whenever you turn the screw, the lower plate has been adjusted. Whenever you turn the screw, the upper plate gets adjusted. Okay. Then there is a plate bubble. Two plate bubbles are mounted at a right angle to each other uh, on the upper surface of the vernier plate. One bubble is kept right parallel to the horizontal axis of the theodolite. Sometimes one plate bubble is provided on the vernier plate. The bubbles are meant for leveling the instrument at the type of measuring the horizontal angle. So the basic reason why we are providing plate bubbles are is that whenever you take observation, the basic aim is that, yeah, the line of collimation should be perfectly horizontal. In order to check that whether it is horizontal or not, your bubbles have been provided. Okay. Then there is a standard or A frame. Okay, so two frames are provided on the upper plate to support the telescope. The vertical circle and the vernier scale. These frames are known as the standard A frame. Okay, so you can see that this is a diagram in which you can see that this is a frame which is similar to your alphabet A. So this frame has been provided which is supporting the whole telescope. Okay, then there is telescope. Telescope is pivoted between the standard at right angles to the horizontal axis. It can be rotated on its horizontal axis and in vertical plane. So you can rotate your telescope in the horizontal axis as well as in the vertical plane. The telescope is provided with the focusing screw. So basically, you can focus with the telescope. You can see the object which is far with the help of telescope. Okay, some clamping screws are provided to take accurate measurement, and some tangent screws are provided for taking some accurate measurement. Okay, after that there is a vertical circle. A vertical circle is rigidly fixed with the telescope as it moves with it. Okay, so whenever you are rotating your telescope, your vertical circle revolve along with it. Okay, so it is divided into four quadrants. Each quadrant is graduated with 0 to 90 degree. Okay, in opposite direction, with zero mark at the end of the horizontal diameter at the vertical circle. Okay, so basically you can measure up to an angle of 0 to 90 degree on your vertical circle only. Then there is index bar or T-frame. So the index bar is provided on the standard in front of the vertical circle. It carries two vernier CND at the two end of the horizontal arm. The vertical legs on the index bar is provided with the clip screw at the lower end by means of which altitude bubble can be brought to the center. Okay. After that, there is altitude bubble. A long sensitive tube is provided on the top of the index bar. This bubbles is brought to the center by the clip screw at the time of measuring of the vertical angle. So while performing measuring vertical angle, you will have to adjust the altitude bubble. Then there is sometimes compass also provided. Sometimes a circular compass is mounted on the vernier scale between the standard. In a modern theodolite, an adjustable through compass or a tubular compass can be fitted with the screw to a standard. After that, the temporary adjustment of theodolite. So how you will have to perform the temporary adjustment of theodolite. So basically, the setting the theodolite over the station, the tripod stand is placed over the required station. So what you have to do, at the point at which you have to fix your theodolite, you will have to open the tripod stand on that. The theodolite is then shifted from the box and fitted on the top of the stand by means of wing nuts according to the fixed arrangement provided along with the instrument. So what you have to do, because generally your satellite is provided in a box, you will have to open that box and you will have to arrange fix with the tripod stand. Okay, there are some socket arrangements with the help of which you can fix your tripod stand with your satellite. After that, this is the first position. You can see that there is a tripod stand on which a theodolite has been mounted. Then after that, first you will have to do what? You will have to perform approximate leveling with the help of tripod stand. Okay, so the legs of the tripod stands are placed well apart, firmly fixed on the ground. Okay, then approximate leveling is done using this stand. To do this, what you have to do is that you have to fix the two legs which are kept firmly fixed on the ground, and the third one is moved in and out clockwise or anti-clockwise so that the bevel approximately comes into the center of the run. So what you are doing is that you are fixing the two legs, and with the help of the third leg, you are rotating the third leg clockwise or anti-clockwise direction, so that approximately the bubbles come to the center. So this is the photo of your temporary leveling. After that, centering. So for exactly marking the station which is on the ground with the theodolite, what you have to do is that sometimes plumb bobs are provided with the theodolite box. So you will have to what? Fix the plumb bob at the center of your theodolite, and it should be matching with the center of the point. Okay, once it has been done, that means your centering has been complete. So centering is the process of setting up of the instrument exactly over a station. At the time of approximate leveling by means of tripod stand, it should be ensured that the plumb bob suspended from the book under the vertical axis lies approximately over the station peg. Okay, so this is how your centering has been done. After that, leveling. Now temporary leveling is been done. Now you will have to permanently level it before taking the observation. Okay. So before starting the leveling operation, all the foot screws are brought to the center of the rod. So as I've told you previously, it consists of 3 foot screws. Okay. So before starting the leveling operation, all the foot screws are brought to the center of the rod. Then the following procedure is adopted. The plate bubble is placed parallel to any pair of the foot screws. What you have to do is that the plate bubble is kept parallel to the 2 foot screws, and then by turning this foot screw inward or outward equally, the bubble is brought to the center of its rod. After that, this operation is been done. Then what you have to do is that then the plate bubble is turned through 90 degrees so that it is perpendicular to the line joining the first and the second foot screw. So what you have to do is that after they are getting parallel to the 2 foot screw, then you have to make the telescope parallel perpendicular to the third foot screw, and you will have to turn that foot screw inward or outward until your bubble is coming to the center. Okay, once these two operation has been done, you will have to rotate the telescope through 360 degree and see that at every point your bubble is at the center. Okay, once the bubble is at center, that means your leveling has been perfect, and if it is not, you will have to perform the same procedure. Okay, so that your bubble comes to the center at every point. Okay, this is how your leveling has been done. So this is a picture in which you can see that the bubble has been kept parallel to the 2 foot screw, which is A and B, and then this foot screws are being turned inward and outward so that this bubble comes to the center. After that, in the next position, you can see that it has been brought perpendicular to the third foot screw, and now this third foot screw has been rotated inward and outward until this bubble is coming to the center. Okay, after this, the telescope has been revolved to 360 degree, and it has been checked whether all point your bubble is at the center or not. Once it is at the center at all the point, that means your leveling has been perfect. Okay, you can take your observation further. Okay, after that, sometimes some instrument may have two plate bubbles perpendicular to each other. In such case, one bubble is kept parallel to any pair of the foot screw, the other partly bubble. Plately bubble will be automatically be perpendicular to the position of the first bubble. Here, the instrument need not to be turned. The first bubble can be brought to the center of by turning the first and the second foot screw, and the second bubble can be brought to the center by turning the third foot screw. Okay, this is in case of two plate bubbles. The process is repeated several times so that the bubble remains in the central position of the plate bubble, both directions perpendicular to each other. The instrument is rotated through say 360 degree about its vertical axis. So instrument is rotated through 360 degree in the vertical axis. If the bubble still remains in the center of the position, the adjustment of the bubble is perfect, and the vertical axis is truly vertical. After leveling, what you have to do is that you need to focus the eyepiece also. Okay, so because eyepiece is also important while taking observation, the crosshair should be clear and distinct. So for that purpose, what you have to do is that you have to keep a blank paper in the front of the telescope. Okay, and then you have to turn the eyepiece clockwise or anti-clockwise until the crosshairs are clear. Okay, once the crosshairs are clear, you can take your observation. Okay, this is about your eyepiece. After that, setting the vernier at 0 degree. Okay, so before you take horizontal angle or before you take your vertical angle, you need to fix the vernier at 0 degree and vernier B at 180 degree. To do this, what you have to do is that uh, lower clamp has been fixed. First, you need to fix the lower clamp. Then the upper clamp is loosened, and the upper plate turns until the arrow of the vernier. Okay, so when you release the upper clamp, you turn the telescope. Along with your telescope, your upper plate also move. Okay, now A is approximately coinciding with zero, so you need to approximately coincide A with your zero, and the vernier B approximately with your 180 degree. Okay, when the upper plate is clamped, now you have to fix the upper plate, and by turning the upper tangent screw for little measurement, for little movement, you have to use your tangent screw. Okay, so upper tangent screw has been now rotated so that it exactly matches with 0 degree at vernier A and 180 degree at vernier B. Okay, so you can see that this is a diagram in which you can see that the graduations have been marked. This is 10, 20, 30. Okay, so you need to fix the position A with exactly coinciding with the your 0. Okay, so once you have done your setting of the vernier, you can now take your measurement, that is your horizontal as well as your vertical angle. Okay. After that, there is permanent adjustment of theodolite. So a theodolite consists, as I've told you, it consists of several fundamental lines, and they have certain desired relationship between them. And because of excessive use and improper handling of the instrument, these relationships between the fundamental axes get disturbed. And if these fundamental axes get disturbed, you will have to do the permanent adjustment. Okay. Otherwise, you will not get the proper reading. So okay, so in order to understand how to do the permanent adjustment, you will first need to understand what are the various fundamental lines, okay, and what is the desired relation between them. Okay, so first we need to understand this fundamental lines. Okay, so the fundamental lines which are generally used in your theodolites are your vertical axis. You can see that there is a vertical axis along which your theodolite moves in the horizontal plane. Then there is axis of the plate level, okay, the line which is parallel to the plate bubble. Then there is line of collimation with the line which is passing from the center of the object glass and the center of the optical glass. That line is called as the line of collimation. Then there is horizontal axis. Okay. Then there is bubble line of the altitude level. So these are the lines, some of the lines, fundamental lines which are being used in your theodolite. Now, what are the desired relationship between them? The first relation between them is that the axis of the plate level. Okay, so the plate level axis must be perpendicular to the vertical axis. So this is the first and basic desired relation, which is what the plate level axis must be perpendicular to the vertical axis. The second one is that the line of collimation should coincide with the optical axis of the telescope. So the line of collimation and the optical axis of the telescope, they should coincide with each other, and it should also be perpendicular to the vertical axis, and they together should also be perpendicular to which the vertical axis. Next one, the axis of the telescope must be parallel to the line of collimation. Okay, so the axis of the telescope must be parallel toward the line of collimation. Okay, the line of collimation must be perpendicular to the horizontal axis. Okay, so the horizontal axis and the line of collimation must be perpendicular. Okay, and the vertical circle should read zero when the line of collimation is horizontal. So whenever you are taking the observation, the line of collimation, it should be what, zero shown on your vertical circle whenever you are taking any observation. Okay, that means your line of collimation is perfectly perpendicular to the horizontal axis. So these are the four relation between the fundamental lines which has been provided in your theodolite. Now, how to do the permanent adjustment? There are different methods to do permanent adjustment. So the first one is to make the axis of the plate level perpendicular to the vertical axis. How to make this plate axis perpendicular to the vertical axis? The following procedure has been adopted to the first adjustment. The first one is that the theodolite has been set up firmly on the ground with its leg apart and firmly fixed on the ground. So you need to fix the theodolite firmly into the ground with the help of your tripod stand. Then after that, the plate bubble is made parallel to any pair of the foot screw. Okay, and then the bubble has been brought to the center of its run. What you have to do is you have to perform your leveling operation. Plate the bubble has been made parallel to any of the foot screws, two foot screws, and they are being moved inward or outward, and then the bubble is coming to the center. Then the next one is the telescope has been turned toward the third foot screw. Okay, that is mean it has been made perpendicular to the third foot screw, and the third foot screw has been rotated until the bubble is coming to the center or not. Okay, the process is repeated. This process is basically repeated several number of times until your bubble is perfectly into the center. Okay, so you need to repeat this procedure several times so that your bubble is exactly at the center. Now, if the bubble is turned through 180 degree about the vertical axis, if the bubble still remains in the central position, so if you're turning the telescope by what, 180 degree, and if the bubble is again still at the center of its run, then the axis of the bubble is perpendicular. That means that the axis of the bubble is perpendicular to the vertical axis, which may be assumed to be truly vertical. That means, suppose if they are coming exact, if the bubble is coming exactly at the center, even after you have turned the telescope through 180 degree, so that means your instrument is perfectly adjusted. That means you don't need to perform any type of adjustment. Okay, And suppose if you're turning the telescope by 180 degree and if it is not coming to the center, that means your instrument is not in perfect adjustment. You will have to perform some perfect adjustment, okay, so that your desired relationship is maintained. So okay, suppose if it is not coming to the center, what is the procedure to be adopted? If the bubble does not remain in the center, in the central position, the amount of deviation is noted. So what you need to do is that by how much amount it is deviating, that you need to note it down. So suppose say the deviation is by twice n. So you have noted that the division is coming out to by twice n. So how to make this 2n depleted? So for that, what you have to do is that half the deviation is adjusted by the help of capstan head nut provided below the bubble tube. So there is a nut provided below the bubble tube, so that half division is been adjusted with the help of this capstan head screw, and the remaining half of the uh, division has been adjusted with the help of your temporary leveling. That is the process of repeating several times until the bubble remains into the central position for any direction of the bubble tube. So okay, so half deviation is adjusted with the help of capstan head screw, and half deviation is adjusted with the help of your leveling operation. Okay, so this is how you will have to maintain the relation between that is your first relation between your plate level perpendicular to your vertical axis. This is how your permanent adjustment has been done. After that, the next one is to make the line of collimation coincide with the optical axis. So if you want to make the line of collimation coincide with the optical axis of the telescope, first the horizontal and then the vertical hairs are adjusted. So you need to adjust the vertical as well as the horizontal hair. Okay, so how the adjustment of horizontal hair has been done? Three pegs are driven into the ground at T, A, and B as at a known distance apart. So you can see that in this diagram. uh, Three pegs are been fixed at point T. There is your instrument at point A. There is your leveling staff at point B. There is your leveling staff. Okay. After that, the theodolite is been set up at point T, and after proper adjustment of staff, the readings are taken on A and B. Suppose the readings are A and B B1. So you, from point T, you can see that at point A you have taken an observation which is coming out to be A. At point B you have taken an observation which is coming out to be B B1. Okay. So this is observation at point A, that is capital A, small a, and this is the observation at point B, capital B, B1. Now by transiting the theodolite, the staff readings are taken on A and B. Okay, so what you need to do is that you are transiting instrument, you are turning the instrument by 180 degree, and again you are taking the reading on A and B. Suppose the readings are coming out to be A and B. So if the readings on the second observation tallies with those of the first horizontal layer, that means your instrument is in perfect adjustment. That means your horizontal hair is in perfect adjustment. Okay, so if you're turning the telescope by 180 degree and again you're taking the readings on A and B, and if it is matching with the previous reading, that means there is no need to make any adjustment in the instrument. Okay, if the second observation gives a new reading, so suppose if you're turning the telescope by 180 degree and it is and that readings are not matching with the previous reading, then what you have to do is that say BB2, suppose the reading which is coming out at point B is BB2, then the horizontal hair is required to be adjusted. So what you need to do, you need to adjust the horizontal hair. The next one is the adjustment for your vertical hair. Now how to do the adjustment in the vertical hair? So now the theodolite is been set up at point T. After proper leveling, a ranging rod has been fixed at A. So how to do this vertical hair adjustment? And now the theodolite has been set up at point T, and now after proper leveling, a ranging rod has been fixed at point A by looking through the telescope, keeping the upper and lower clamp fixed. Okay. Okay. Now the instrument, as you can see in this diagram, the point T. Okay, the instrument has been fixed at point T. You're taking the reading on point A on this ranging rod. After that, by transiting the telescope, the ranging rod is being fixed at point B. Now you need to turn the telescope by 180 degree and you need to fix a new point which is called as point B on which your ranging rod has been fixed. Now the upper clamp is loosened, and by turning the vernier plate, the ranging rod at A is again bisected. Now what you have to do is that you need to release the upper clamp and you have to turn the telescope again, and you need to bisect the ranging rod at A. Suppose if the ranging rod at B is seen bisected after transiting the telescope, the vertical hair is in perfect adjustment. So again you have to turn the telescope and see whether the point B has been bisected or not. If it is bisected, that means your vertical hair is not required any adjustment. If it is not bisected, that means your instrument need to be adjusted in vertical hair. If not, the amount of error has been noted, let BB1 be the total error. Suppose if it is not matching with your this point. So suppose there is a new point BB1. Okay, so BB1 has been marked. This is BB1 is the total error. Okay, the position is marked by the ranging rod at B, where BB1 is one fourth of the total error. Okay, so BB1 is coming out to be the one fourth of the total error. The vertical hair is shifted by turning the horizontal diaphragm screw to bisect the ranging rod at B. Now, with the help of some instrument, what you have to do with the help of some screws, you will have to adjust the vertical hair so that it is bisecting with your point B. Okay, during the adjustment, one fourth of the total error is taken into consideration because the actual error is magnified four times. The telescope was turned twice in the vertical plane because you have turned the telescope twice, so the total error is taken as one fourth. After that, there is the third adjustment to make the horizontal axis perpendicular to the vertical axis. So if you want to make the horizontal axis perpendicular to the vertical axis, the following procedure is adopted for making the necessary adjustment. The theodolite is set up at point T from some distance away from pole P. Okay, so in this diagram you can see that the theodolite has been fixed at some distance from point B. Okay, after that the plate bubble is perfectly level. Now you have to do the temporary adjustment, that is leveling has been done. Now looking through the telescope, a well defined point A is marked on the pole. The upper and the lower clamp is are kept fixed. So what you are doing in this is that with the help of the clamping screw, you are taking a reading observation and point A has been fixed on this ranging rod. Okay. After that, now the telescope is lowered and another point B has been marked near the base of the pole on the same line of the side. You can see that there is another point which has been marked below the point near the base of point B, which has been marked as point B. After that, the upper clamp is loosened and the telescope has been turned through 180 degree. Now the upper clamp has been loosened and the telescope has been turned through 180 degree by transiting it. Okay, then the marking A is been bisected. Again, you have to bisect A. Now the telescope is then lowered. If the line of sight bisect the mark at B, then the adjustment is perfect. So if it is exactly matching with the point B, then there is that means that the adjustment is not required. If it is not matching with point B, then you need to what you will have to perform adjustment so that it is been bisecting exactly with B. If not another point B, B has been marked on the ranging rod. Suppose if it is not matching with B, what you have to do is that you have to mark a point R on the same level as B. So you can see that you are marking with another point R as point B. Now how to adjust this? Point A and C are marked midway between B and B dash. So point C has been marked midway between these 2 points. Suppose B is somewhere here and this capital B is somewhere here. So you have to mark midway between these 2 points as your point C. Okay. After that, the point C is bisected by the telescope and the upper clamp has been tightened. Now you have to bisect the point C and then the upper clamp of the telescope has been fixed. Now the telescope is now raised. Uh, this time the line of sight will be not bisecting point A. Now the telescope is now raised. This time the line of sight will not bisect A. The adjustment end of the horizontal axis is raised or lower until the line of sight bisect the point A. This procedure is repeated several times until the correction is perfect. Okay, so this is how you will have to perform your adjustment. So these are all about the adjustment. Now there are some type of modern theodolites which are available, okay, which have higher magnifying values, which are used for space purposes. One is your watt micro optic theodolite. This is the diagram of your watt micro theodolite. Then there is wild T2 theodolite. Okay, this is the photograph of your wild T2 theodolite. Okay, then there is wild T3 precision theodolite. Okay, this is a diagram of your wild T3 precision theodolite. Then there is wild T for universal theodolite. This is a picture of your wild T for theodolite. These are the instruments which are used for higher accuracy, and it is generally used as space purpose and space marking. Okay. Then there is tailstock theodolite. This is the diagram of your tailstock theodolite. Now, what are the errors which can be occurred while performing your theodolite survey? So there may be some instrumental error. Okay, so instrumental error. There might be some non-adjustable of plate bubble. So while performing the theodolite serving, the plate bubble is not coming to the center. That will cause some error to your reading. This error may be eliminated by what leveling, and if leveling has been not done properly, it will affect somewhere your readings. Okay, after that, the line of collimation not being perpendicular to the horizontal axis. Okay, so it might cause some error because every time you perform your theodolite traversing, the line of collimation should be perfectly horizontal. Okay, otherwise your reading will be wrong. Next one, in this case, the cone is formed when the telescope is revolved in the vertical plane, and this causes an error in the observation. Okay, the error is eliminated by reading the angle from both the face, that is left and right, and the average of the reading has been taken. So what you have to do is that you have to take the observation with the help of face left position as well as face right position. Then you will have to take the average of these two values, that will give you the perfect reading. After this, horizontal axis not being perpendicular to the vertical axis. Okay, horizontal axis not being perpendicular to the vertical axis. If the horizontal axis is not perpendicular to the vertical axis, there is an angular error. So this is eliminated by reading the angle from both the faces. Then there can be line of collimation not being parallel to the axis of the telescope. If the line of collimation is not parallel to the axis of the telescope, there is an error in the observed vertical angle. So this error is eliminated by taking reading from both the faces. So you have to take reading from both the faces and take the average of these two values. Okay, that will give you the correct answer. After that, there is eccentricity of inner and outer axis. This condition causes an error in vernier reading. Okay, this error is eliminated by taking reading from both the vernier and considering the average reading. Now, graduation being not uniform, the error is due to the condition. The error due to this condition is eliminated by measuring the angle several times on different part of the circle. After that, there is vernier being eccentric. The zeros of the vernier should be diametrically opposite to each other. Okay, so when the vernier A is set at 0, the vernier B should be 180. But in some cases, this condition may not exist. This error is eliminated by reading both the vernier and taking the average of that readings. Okay. After that, there might be some personal error which may cause error in your readings. Okay, so there might you while performing the theodolite traversing, you may not have done the centering properly. That may cause an error. Okay, the object of the ranging rod may not be bisected accurately. That may cause an error. The error would be from the result in the vernier are not readed. Okay, so the reading, if you are taking the reading which is not proper, then it will cause an error to your observations. Then there are natural errors. Sometimes high temperature causes high error due to irregular refraction. Then there is high wind causes vibration in the instrument, and this may lead to wrong reading on the vernier. After that, there are different methods of your horizontal angle. How to measure your horizontal angle? Suppose an angle AOB is to be measured. The instrument has been set up at point O. You can see that in this diagram. Your instrument has been set up point O. Now, after performing your temporary adjustment, that is centering, leveling, all that, what you have to do is that you have to first pick the lower clamp and release the upper clamp. You need to turn the telescope and make the vernier exactly match with the zero. After that, the upper plate has been fixed. Now the lower clamp has been released and point A has been marked. once point A has been bisected, well, you need to release the upper clamping screw. You need to turn the telescope so that it has been bisecting with point B, and then you can directly see the angle on your vernier scale. Okay, that will give you the correct horizontal angle. Now this observation has been done with first in the first step by keeping the vertical circle on the left hand side with the face left position, and then you will have to perform the same operation by keeping the vertical circle on the right hand side. That will be called as your face right position. So by taking the average value of the face left observation as well as the face right observation, you will get the correct exact angle of angle AOB. This is how your horizontal angle is been done. After that, there is a repetition method. In this method, what you have to do is that, let me show you the diagram. Okay. Now two ranging rods have been fixed. One it has been marked at point A, another one has been marked at point B. Okay. Your instrument, your theodolite has been fixed at point O. After performing the temporary adjustment, that is your centering. After that, your leveling. Okay. Now focusing of your eyepiece, focusing of your theodolite. What you need to do is that you need to fix the lower clamp and you need to release the upper clamp, and you have to make the vernier exactly at zero. So the reading on the vernier A should be zero, and at vernier B it should be exactly 180 degree. Once it has been set at 0 degree and 180 degree, what you have to do is that you may need to fix the upper clamp and you need to release the lower clamp, so that by turning the telescope you can bisect the ranging rod at A. Once you have bisected the ranging rod at A, you need to what uh, release the upper clamp, okay, and you need to swing the telescope toward the right hand side so that you can bisect the ranging rod at B. Okay, once you have bisected the point B, you will directly read the angle which is coming to your vernier scale. Okay, suppose the angle it is coming out to be suppose 30 degree. So you have taken 30 degree, you have written 30 degree on your paper, that the angle AOB for the first step was coming out to be 30 degree. Now what you have to do is that again you need to fix the upper clamp and you need to release the lower clamp. Then turn the telescope and again bisect the ranging rod at A. Now the vernier at this point will show you the angle 30 degree at point A. Okay. After that, you will again have to release the upper clamping screw, and then you need to swing the telescope towards B until point B has been bisected. Once point B has been bisected, you need to fix the clamp and you need to take the reading from the vernier A. So the reading will be coming exactly twice the first angle, which is coming out to be 60. Again, fix the telescope. Again, fix the upper clamping screw, release the lower clamping screw, turn the telescope, and again bisect the ranging rod at A. At this point, the reading at point A will be 60, first point, and then you need to again release the upper clamping screw and swing the telescope towards point B. Okay, once you have bisected point B, the angle will be what? Thrice the first value, which is 90 degree. Okay, so in this way you are repeating the procedure from 0 to 30, from 30 to 60, then 60 to 90. So this procedure is called as your repetition method. And the final reading is given by what? Whatever the final value you are getting, that is you are getting the final value as 90 degree. You need to divide it by the number of steps. So how many steps you have done? You have done one step, two step, and three step. So 90 divided by 3. That will give you the exact angle of your AOB. This method is called as your repetition method of measuring your horizontal angle. After that, as I've told you, generally observations are done with the help of face left position and face right position, and then the average of these two values are taken. Okay. Then there is a next method which is called as your reiteration method. Okay. So reiteration method is generally used when you need to cover a total horizon. Okay, so what you are doing in this is that you're fixing the telescope at point O. After performing temporary adjustment, you're making the vernier zero. Okay, then you are bisecting the ranging rod at A. Then you are swinging the telescope in the clockwise direction so that it can be bisected, so that the point B can be bisected. Okay, so the readings of point B has been marked. Okay, after that, again you are swinging the telescope from B towards point C. Okay, and again the observation has been done. Okay, after that, again you are turning the telescope from C to point A, and you are making a complete revolution, which is your 360 degree angle. So you are basically starting from zero, and you are completing an angle at 360 degrees. So okay, in this way you're completing one full horizon. Okay, this procedure is called as your iteration method. First reading has been taken with the help of face left position, and the other reading has been taken with the help of face right position, and then the average of these two values are taken, which will give you the perfect horizontal angle. After that, vertical angle. As I've told you, your theodolite can be used to measure horizontal as well as vertical angle. So with the help of theodolite, you can also measure vertical angle. So the vertical angle is the one between the horizontal line. Okay, if you are taking the angle which is above the line of collimation, then it is called as your angle of elevation. And if you're taking an angle which is below the line of collimation, then it is called as your angle of depression. Okay, so if you're taking above, it is called as elevation. If you're taking it below, then it is called as your depression. Okay, consider suppose the angle AOC and that of depression is BOC is to be measured. The following procedure is adopted. So you need to observe two angles, one it is in elevation and one it is in your depression. Now the theodolite is set up at point T, point O. It is centered and level properly. The zero of the vernier at C and D are set. Okay, marked on the vertical circle. Now the plate bubble is brought to the center with the help of foot screws. The altitude is brought to the center by means of clip screw. At this position, the line of collimation is exactly horizontal. So you need to firstly make the line of collimation perfectly horizontal before taking the observation. Now to measure the angle, the telescope is raised slowly to bisect the point A accurately. The reading on the both the vernier are noted and the angles of elevations are recorded. You will directly get the angle from in case of vertical angle. Okay. Now the face of the instrument is changed and the point A is again bisected. The reading on the vernier are noted. The mean of the angle is observed and assumed to be the correct angle of elevation. As I've told you, in surveying with the help of theodolite, what you have to do is that you have to take two observations, one with your face left position, one with your face right position, and then the average value of these two angles are given, and that will be the correct angle. And the same procedure is adopted to measure the angle in case of depression. Okay, the next is your computation of latitude and departure. Now the theodolite is not plotted according to the interior angle or the bearings. In compass, what you used to do is that we generally use your angles, that is your bearings, to mark the traverse. But in case of your theodolite, generally do not use your bearings. We use the latitude as well as the departure. The plotted by computation the latitude and departure of the point and then finding out the independent coordinates of the point. So in the theodolite traversing, we need to find out the latitude and departure of the lines, and with the help of that, your traverse has been plotted. The latitude of the line is the distance measured parallel to the north-south line. So latitude is representing your north-south line. The departure is representing your east-west line. Okay. Now the latitude and the departure of the lines are also expressed in the following way. So suppose if you are writing as nothing, then the latitude is toward north and it is taken as positive. And if it is southing, the latitude is towards your south and it is taken as negative. Then if you are taking your departure and easting is coming, so easting is positive. Your westing is what? Departure is your negative. Okay. So this is a basically a conversion of your whole circle bearing to reduced bearing. This I've already taught you in your compass survey. Now, the computation of latitude departure. The theodolite is not plotted according to the interior angle, as I've told you. I think this is the same side. Okay. In this, you can see that there is a traverse given or a line given AB. Okay. This is the north-south pole. This is your east-west pole. So line AB will have a certain length. Okay. So the length has been marked as L. Now the reduced bearing is what? North and some angle. So whatever this angle may be, east. So this side will be what? L cos theta. This line representing north-south line is represented as L cos theta. The line which is representing your east-west line is called as your departure, which is given by your L sin theta. Okay. So in case of first quadrant, it will be L cos theta. this will be L sine theta. In case of second quadrant, that means southeast part, it will be minus L cos theta. This will be what? Positive L sine theta. In case of this side, that is your southwest side, it will be L cos theta and minus L sine theta. And in northwest direction it will be L cos theta and negative L sine theta. So this is how your quadrant represent your latitude and departure when you have to take it positive. Whenever north is coming, you have to take it positive. Okay. In case of east, it is taken as positive. In case of south, it is negative. In case of east, it is positive. In case of south, it is negative. In case of west, it is negative. And in case of north, it is positive. And in case of west, it is negative. Okay. So this is how you will have to give the notations, which is your positive and negative side. After that, there is coordinates. You need to convert these coordinate while drawing your traverse. One, it is called as a consecutive coordinate. One is your independent coordinate. The latitude and the departure of a point calculated with reference to the preceding point. So if you are finding out the latitude and departure of the point with the help of the preceding point, with reference of the preceding point, then that type of coordinate is called as the consecutive coordinates. Okay. If you are talking about independent coordinate, the coordinates of any point with respect to the common origin. So if you are taking a common origin and you are marking the points, okay, their coordinates, then that type of coordinate system is called as your independent coordinate system. Now, balancing of the traverse. In case of closed traverse, the algebraic sum of the latitude must be equal to zero, and that of departure must be equal to zero in an ideal condition. So this is for balancing of traverse. So in case of closed traverse, the sum of the latitude must be equal to zero, and the sum of the departures must be equal to zero. In other words, the sum of northing must be equal to the sum of the southing, and sum of the easting must be equal to sum of the westing. But in actual practice, some closing error may always found to be exist while computing the latitude and departure of the traverse station. Okay, so at in practical example, it won't be possible that you will get exactly your starting point and end point coinciding with each other. There will be some error. Okay, that is called as your closing error. Okay, so the total error in latitude and departure are determined. So how much error is coming in the latitude and departure, that has been determined, and these errors are then distributed among the traverse stations. So how many stations are there? Depending upon that, these error will be distributed among all the stations. Okay, there are certain rules which are being followed. One is called as your body's rule. Okay, in this, what you have to use this formula for finding out the correction in the latitude. That is, the correction of latitude of any side is given by the length of that side divided by the perimeter of the traverse into total error in latitude. Then correction in the departure of any side, length of that side divided by the perimeter of the traverse into the total error in your departure. So body's rule, this type of formulas are used. Then there is transit rule. In this, the correction of the latitude of any side, the latitude of side is divided by the arithmetical sum of all the latitude, and then it is multiplied by the total error in the latitude. Then in case of departure, departure of that side divided by the arithmetical sum of all the departures into the total error in the departure. This is your transit rule formula. Then there is third rule formula. Now correction in this, you have to do it separately. You have to do the correction in northing separately, southing separately, easting separately, westing separately. Okay, so northing of that side divided by the sum of the northing into half the total error in latitude. Then after that, correction to the southing, southing of that side divided by the sum of the southing into half the total error in your latitude. Okay, now correction to the easting of any side, easting of that side divided by sum of the easting into what, half the total error in your departure. After that, correction in the westing of any side, westing of that side divided by the westing of sum of the westing into half the total error in your departure. So these are the four formulas which are used in third rule. Okay, if the error is positive, the correction will be negative and vice versa. So if the error is coming out to be positive, the correction will be what, negative. So if the error is negative, the correction will be of positive. Okay, and based on this type of your rules, there are some numericals also asked. Okay, that we will discuss in some other class. Okay, this is all for today. Okay, we'll see you in the next class. Thank you so much.